This is topic 3 in Unit 2, the multiplication rule of probability. So just to recap, when you're doing a probability problem and you have the word or, you want to associate the word or with addition. So we talked about how there is an overlap problem, and you can either accommodate from that by using the formula or by making sure that when you construct your probability, you don't double count. We're going to have some new terms before we get into our new rule. First is independent events. Two events are considered independent if the occurrence of one does not affect the probability of the other. So basically, they operate completely separately. Example is the game Yahtzee. So if you're familiar with Yahtzee, you roll 5 dice and then you choose some to keep, you choose some to re-roll. And when you re-roll those die, one of them isn't going to be like, oh, hey, the first one is a 6. I don't want to be a 6 again. That's not how it works. So they don't affect each other. So these die rolls are an example of independent events. On the opposite end of this, dependent events. Two events are considered dependent events if the occurrence of one affects the probability of the other. So just like if you claim a dependent on your taxes, you are in charge of that person. You know, what you do affects them and what they do affects you and vice versa. So an example of this is just about every single card game that I can think of, where once one single card has been dealt out, every single probability in the rest of the deck changes. It changes by a little bit, but it does change because there's no longer 52 cards. There's now 51 cards, or if you're in the middle of dealing, then there's even a more complicated procedure to think about. These two are going to be pretty important when it comes to our new rule today. So it's a question you're always going to want to ask yourself. Are my events independent or dependent? So formally, there's no fancy demonstration for this one, but formally the multiplication rule says, we have new notation here. I personally don't emphasize this notation. I think it's more important to just think about what happens when event A has already happened. But probability of A and B is equal to the probability of A times the probability that B happens given that event A has already happened. So I know that sounds a little convoluted there, but P given A, that bar up and down is called red given, and it's the probability that B happens given that event A happens. So for example, if you're digging in a drawer and you're trying to get, a pen out of it, it's a drawer filled with pens. If you take one and it's not the pen you want and you put it back, you still have the same probability of selecting the pen that you'd like. Whereas if you take one of those pens out, it's not the one, and you put it aside, everything else inside there has changed. So by removing that first pen, you've completely changed the environment, basically. It's no longer the same exact drawer with the same exact pens. So again, the consideration that you want to take, this correlates exactly to independent and dependent. So if you're selecting people or items with replacements, the events are independent because you're putting them back. So for example, when I took my pen out and I returned it, nothing has changed in my drawer. Maybe the pen is in a different location, but overall it's still the same, population, pens in a drawer. Whereas if you take it out and you keep it, so that means you're selecting without replacement. The events are considered dependent. So that means the second pen depends on the first one that you took out. So if you wanted to get 2 red pens and the first pen you took out was red, well, the whole entire environment has changed. So that's something that we will look at when we get to an example specifically. So one thing that we kind of need to take with us that's, in a lot of cases it's assumed, which is slightly dangerous, is the 5% guideline. The 5% guideline says that if a sample size is 5% or less of the total size of the population, events might be treated as independent. When we look at an example, this statement will become pretty clear, but for now it's kind of on the, the funky end. So this is important for a number of things. Sometimes we cannot possibly figure out a probability changing. So for example, if I took one person in the United States, so we're in Wyoming here, and I took somebody from Florida and I put them on a boat, a rowboat, and no oars, and I just pushed it out to sea. And if they slowly drifted away, the whole entire United States, if you didn't know that person, doesn't feel any different. So by removing that one item, the population is generally unchanged. Whereas if you have, 5 people in your household and one of them goes missing or is suspiciously quiet, you'll notice because it's a pretty significant amount of your household compared to the whole size of it. So 1 out of 5 people going missing, you'll probably notice. 1 out of 300 million people going missing, if you didn't know them, sorry person, but we probably wouldn't notice. So in formula form, which does kind of start to make this a little bit more clear before we get to an example, the sample size divided by the population size is again what we're comparing. So how much is the part compared to the whole? If that difference is really, really small, then the probability probably won't change very much anyway. And we'll see this in a few examples. So, exercise 1. When going to an exam, and this is the stereotypic probability example. If you Google probability, I guarantee you there will be a teacher that is blindingly pulling a pen from a drawer. So the teacher reaches into the drawer. There's 3 red pens, 4 blue pens, and 2 purple pens. If 2 pens are randomly selected with replacement, that means we put them back. What is the probability that they are both red? 2 pens are randomly selected without replacements. Find the probability that both are red. So for part A, we replaced the initial pen, so the environment has not changed. So we have 3 pens that are red out of 4, 5, 6, 7, 8, 9 total. And then we put it back, right? We haven't changed anything. And let's assume we put it back and it randomly shakes up at dropping the pen back in. So then we have the same situation where there's 3 red pens out of 9 total. So be careful when you multiply this. This is 9 out of 81. There's going to be times where you'll have a fraction down here and you'll put a 9 on this bottom one, which wouldn't make a lot of sense if you actually did that calculation, but it happens pretty frequently. So this is 0.1 repeating. If you put the 1 with the line on top, that is again technically more accurate than rounding to 4 decimal places. But I'm going to stay pretty consistent. I'm going to round to 4 decimal places almost every time. This is a tangible number that I can work with, is the reason why. Whereas this is, a number that technically goes on forever. But if we selected the first pen and it was red, so I think about it as we fix the first part of the event. And then we kept it. The probability for the second will change. So we want a red pen and we want a red pen. So we have 2 parts to the event. And signifies multiplication. So we have 3 out of 9 times 2 out of 8 because one of those red pens is gone and then one of the total, that's part of the total as well. So this is 0.8333. Oh, there should be a 0 there. So, or 0.083 repeating. Either one. If you're doing this in your calculator, I suggest using parentheses around your fraction. So I would put parentheses here. I would put parentheses here. But all the time I suggest to use parentheses. They aren't required, but it's a general safety net. So there are going to be some times where the parentheses are required and other times they're not. So it's better to be safe and just use them all the time. So this is another stereotypical example that we will look at. The internet will have this as well. I always like to include these examples because you will see different variations of these, but we will definitely look at the more, relatable examples as well. So you're late to class. You have a few seconds to complete a 4-question multiple choice quiz. You guess randomly, and each question has 5 options. Find the probability that you get each question correct. Are the events independent? Explain. So what I would do is, I call this my structure here. So there's 4 questions, so each question is its own part of the event. So we want to get this question correct, and we want to get this question correct, and we want to get this question correct, and this question. So if you kind of do this self-talk thing that I just did, it will really help you set up the problems. With these probability questions, it's really easy to make small mistakes here and there. So the more organized you are with your thoughts, the better off you'll be. So there's 1 correct answer out of 5. So we're assuming it's a traditional multiple choice, nothing funky. So there's 1 right answer out of 5. And for each question, the same probability remains. And so this is 1/5 to the 4th power. You need to use parentheses in your calculator. Actually, this one you wouldn't because the numerator is 1. But I would start getting used to it. So this is 0.0016. Pretty small chance, it's less than 1% that you get that question correct. Definitely unusual probability, but this is pretty unlikely. Usually if you sat down and you had to guess, you still had some kind of instinct or inclination. These events are independent because the questions aren't connected. It's not a matching question, it's just a multiple choice 1 through 4. So I'll never give you anything where you'll have to assume something wild happens, but in general, the multiple choice questions aren't going to be linked, so they are going to be independent. All right, so the following table summarizes blood groups and Rh types for 100 subjects. These values may differ in other regions according to ethnicity. So if you Google blood types, you will find a table. I'll do this together here. The first link that comes up is a link from the Red Cross. So I find this to be pretty interesting. So first of all, each race has its own breakdown of blood type and group. So this is, I think, is pretty interesting on its own. So they have lots and lots of data on this. This is probably super close to the population values. And so this is also, I like this one as well. It says, how is my blood type determined? So depending on the blood type of your parents, you will have possibility of certain blood types. So if you watch Law & Order or something, they'll get a sample of the child and they'll say, well, the father is type B. He can't be the father. So that's basically how they do this based on this chart. They have this little disclaimer here, which I think is cute. So if you have questions about paternity, don't trust the chart. You got to go to a doctor. But you can trust the chart for the most part. I think it's pretty rare instances that these would not be predictive 100% of the time for the paternity or the blood type of the child. But I just like this chart here. I think it's pretty interesting. I definitely didn't know this until I started researching. I kind of assumed that it would be the same across the board. So, and this is a pretty interesting thing to read that's common information presented in a detailed chart like this. So this is mimicked, this isn't real data, but this is mimicked off from a combination of the races. So if 2 subjects are randomly selected without replacement, so we don't put them back, they're on a list, we either call them and say, hey, can you give blood? They say yes, we make an appointment, we don't call them back. They say no, we cross them off the list. So find the probability that they are both universal red cell donors. So that's type O. Find the probability that they are both AB positive. So that's getting kind of specific in here. So there are 45 out of, this conveniently table is out of 100. There's 45 out of 100 that are type O. And then we've taken that person out. They've either said, yes, I can give blood, or no, I'm unavailable to give blood, and so we don't call them back at this time. So there's 44 out of 99 available after this first person has been selected. So if you remember, this is the probability that this person is type O, given that this person is type O if we go back to the actual notation. So when you put this in your calculator, I would do 45 divided by 100 times 44 divided by 99 with both of these in parentheses. So I definitely would do parentheses around this fraction, parentheses around this fraction. So next, find the probability that they are both AB positive. Well, there's 4 out of 100 that are AB positive, and there's 3 out of 99 that are AB positive. So AB positive is going to be able to donate to less people. So if this happened, this would be, a pretty unusual combination of people that were called in to give blood. So you're in your car with somebody you're trying to impress. Your iPod or your iPhone or your whatever is on shuffle, and you have the Justin Bieber Believe album. It's 13 songs long, and you have 102 songs in total on your iPod or your music player. So this is a long slew of calculations here, and this is one reason why when we get to the second half of this unit, the technology is going to become very appreciated. So I think of this whole thing as 7 pieces. So I would maybe put 7 lines, 1, 2, 3, 4, 5, 6, 7 on my paper. And so there's 89 songs that are not Justin Bieber. So 89 out of 102. That song has come on. And the way that repeat works is that once a song is selected, it's not eligible to be selected again unless you have some kind of special setting. So you tear down 1, 88 out of 101, 87 out of 100, until you've got to your 7th song. When you put all this in your calculator, you'll end up getting 37.31%. I would definitely make sure that you're able to get the same exact value in the calculation. So are the events independent? No, because once the song comes on, it's not eligible to be played again, so it's not able to be selected. So the second song depends on what happened with the first song. So we're assuming they're all not Justin Bieber's, is what we want. Although the new stuff isn't bad, but... So part C asks, does the 5% guideline apply? So we're going to see a more information than you probably want to know about the 5% guideline. But I actually think the 5% guideline is pretty handy. So the original part of this is the sample size divided by the population size. So 7 songs are being selected out of a total of 102. So when you do this division, this 5% guideline is a percent because it's different from probabilities. This is greater than 5%, so the 5% guideline is not going to apply here. So that means that this is too big. 7 is too big compared to 102. So we're going to take this one step further and figure out the probabilities of the first and second fraction. So on the previous slide, there was 89 out of 102 songs that came on first to be selected, and then 88 out of 101 songs for the second. So if you calculate these probabilities individually, they are different by 0.12%, which isn't huge, but you have to imagine that not only are you taking this number and using it once, you're multiplying it by another number and another number. So your error magnifies the more times that you use it. So you don't want to say, oh, hey, 0.12%, that's not very much. Actually, differences like that will end up being very expensive over time, especially if you round incorrectly just as a mistake. So these two aren't different enough to treat them as the same number, which is what the 5% guideline says. So these two are kind of far apart, so we have to treat them as different. Exercise 5. A tire company produced a batch of 500 tires, 20 of which are defective. In my opinion, that is a very, very large amount of defective tires. So if 4 tires are randomly selected for installation, what is the probability that they are all good? So be careful, because a lot of times people just latch on to that 20 that's in the problem, but there's actually 480 out of 500 tires that are good. But it's a really easy mistake to make because you're used to just taking the numbers you have and throwing them all together. So once we take the tire and we put it on a person's car, that's it. We're not going to put it on and then undo it and then put it back on the shelf. So that tire is no longer eligible to be selected. So now there's 479 out of 499, 478 out of 498, and then 477 out of 497. So we want a good tire, and a good tire, and a good tire, and a good tire. So if you multiply all of these, this is an 84.89% chance. In my opinion, this is not high enough for something like tires that depend on safety so much. But the numbers are convenient, which is helpful. So does the 5% guideline apply? Why or why not? So remember, the 5% guideline is the sample size divided by the population size. We are selecting 4 tires out of 500. So the difference here is that this is less than 5%. It's 0.8%. It's less than 1%. So in this case, the 5% guideline applies. Well, what does this mean for our life? Performing the same comparison that we did with the last example, 480 out of 500, our first fraction, is 96%. 479 out of 499 is 95.99%. So the difference between these probabilities is small, and because the 5% guideline applies, then it's small enough to treat them as the same number. So what the 5% guideline means for us is that originally we could have done 480 out of 500 to the 4th power, which means we say, hey, this is a really small difference. Let's just treat these all as the same probability. This seems like it's kind of lazy right now, but there's times in the future where if we didn't have this, we wouldn't be able to make any estimates at all. So it's pretty good that we are able to have a rule like this that we can rely on. Now, the difference overall is 0.0004. So this is a little bit of an upper estimate because we didn't take out any tires. This difference is smaller than it was between 2 of the fractions in the Justin Bieber example. So the 5% guideline doesn't seem like a real lifesaver right now, but again, it's definitely something that we will need to kind of live by in the future. I would make sure that you can repeat everything that is on the slides without having the slides in front of you. If you have any questions, feel free to email me.